Okay, here's section 4.5, linear equations with three or more variables. Um, Most of the linear functions we deal with are going to be two variables. We deal with equations and graphs that live on a two-dimensional plane, but in the real world there are many examples where things have more than two dimensions, like everything you can see, for example. So this is just a brief introduction into the fact that not all math happens on a sheet of paper. It could happen in three dimensions. So here's an example of a three-dimensional or linear equation with three variables. Notice it's still linear because the degree of this equation is 1. We've got 1x, 1y, and 1z. But the addition of the z brings me into three dimensions, basically. So a graph doesn't look like the normal graph that you see anymore. Now a graph has depth to it. Basically, it would like come out of your page. And the way that we draw graphs in 3D, and you will, like I said, one day you will get into a lot more of this. But here's an example of a 3D graph. You still got your x and y, but you've also got the third dimension, z. So this is kind of like looking at the corner of a room. Those dotted lines just extend into the negatives of the x, y, and z, but the main portion of the graph, to try to visualize this thing, which is a 3D graph drawn on a 2D paper, which isn't always easy to see, just kind of draw the corner of a room that you would see if you literally looked at the corner of the room you're in right now. So I usually put x here and y here and z here. It doesn't have to be that way every time. As a matter of fact, in your book, where I have my y, they call x, and where I have my x, they call y, and the z goes up. So why don't I change that just to agree with our textbook, but it doesn't have to be that way necessarily. Okay, so this graph, you can imagine if you just look at the xy, that's like a normal two-dimensional graph, and it's like laying down flat, and the z is coming up out of the ground, and they all meet at the origin. It's just now we have an x, a y, and a z to consider. So we are just barely getting into this, and we're going to graph this linear equation. A linear equation in three dimensions is actually a plane, and whereas a linear equation in two dimensions is a line, we're going to be drawing a plane. So to draw this plane, we're going to draw it by connecting the three intercepts. If I want to find the x-intercept, that means that y is 0 and z is 0. So that means these two are gone, and I'm left with 2x equals 12. So if y and z are both 0, then x will equal 6. So what I do is I go to my graph, and I go on my x-axis and count out 6. 1, 2, 3, 4, 5, 6. And this is my intercept. Okay, so according to this little corner of the room, I'm on the floor, and I'm along the x-axis because y and z are both 0. And if that's true, then I am out 6 along the x-axis. You could do similar if to find the y-intercept, let x and z be 0, and it turns out that y is 4. So along the y-axis, I'm going to go 1, 2, 3, 4. And along the z-axis, hopefully you can tell that that's going to be 3, because if x and y are both 0, then z is 3. So we're just going to draw a small portion of the plane that cuts through this corner of the so-called room by connecting those three intercepts. So now it's like a corner of a room that has sort of a propped up plane in the corner that is cut off by all of the axes and the planes that are formed by the walls of this room. Okay, so like I said, this is just to introduce you to the fact that there can be three variables. We're not going to do anything fancy, anything difficult. This is a whole section right here this is all I'm going to ask you to do with three variables. Okay, so my main focus for this video is a system of equation with three variables. So let's move on to that. So here's section 4.6. This is a system of three equations with three unknowns, or three variables. So like the equation that we just graphed in 3 dimensions, we're looking for the x, y, z point, or triplet, that makes all 3 of these equations true. All right, this would be the intersection of all 3 planes if you were to graph them all. That graph gets pretty much too complicated to draw and view, so we're just going to do this algebraically. So we're looking for three answers here, and these are the x, the y, and the z that make all 3 of these true at the same time. Okay, just quickly, one example of a triplet that makes this first equation true might be 0, 1, 1. Because if x is 0, y is 1, and z is 1, then that top equation equals 6. Okay, so if 0, 1, and 1 made all of them true, that would be my answer. But I'm just wanting to, that's not the final answer. That's just an example of a triplet that makes the first equation true. So I need the one triplet that makes them all true. So the way we're going to find this, and unfortunately for you, this is a lengthy process. It's going to take you a lot of paper and a lot of time. We go linear combination, or the elimination method, or the addition subtraction method, whatever you want to call it. But we just do it several times, and we eliminate a variable at a time. So right now, I don't have any of my x's, y's, and z's whose coefficients match up very nicely. If I can make a few changes and make that happen, I'm going to start by multiplying my second equation by -3. So I'm going to rewrite my first equation as well. Here's my first equation. And my second equation times -3, all parts, both sides, gives me -3x, and that's the reason I chose -3 right there, minus 9y plus 15z equals positive 21. Okay, so again, the reason I chose that is to make the coefficients of x equal and opposite. So now if I add these 2 equations together, I get -5y plus 17z equals 27. All right, so I've eliminated x from one pair of equations, and I've gotten a true statement involving y and z, but unfortunately I still have a y and z. So this is true, but I'm going to have to do a little bit more. Okay, so what I need to do now is eliminate x in a different pair of equations. And the easiest way to do that is going to be to use equations 2 and 3. Okay, you can't use the same pair of equations, you'll just end up with an equivalent statement. So let me rewrite equations 2 and 3, but while I do that, I'm going to multiply equation 2 by -5 this time. And I hope you see why -5, because I want to get rid of x using a different pair of 2 equations. So equation 2 times -5 is -5x minus 15y plus 25z equals 35. And then I'm just going to write equation 3 as is. Okay, when I add these 2 together, get -15 plus 7, which is 8y, 25 minus 3, which is plus 22z, equals 38. All right, so again, I've created a true statement involving y and z, and now this is the system of equations we have been dealing with. We've been doing systems with 2 equations and 2 unknowns. So I'm going to write this, I'm not going to rewrite it just yet. I need to get these 2 equations into a place where I can add them together and eliminate either the y or the z. So it looks like my best option, my most convenient option, is going to be to take this equation and multiply it by 8, this equation and multiply it by 5, and get rid of these y's. Once you get rid of one altogether and solve for one of your unknowns, it's going to be a quick process to get the other 2. So this equation multiplied by 8 is -40y plus, 88 times 17. Got to get my calc. And through the magic of technology, I have found a mistake and zoomed into the future. So here's my mistake. Hopefully you caught it a minute ago. negative 15 plus 7 is negative 8. And I don't know if I've told you this yet, but I only make mistakes like this just to try to catch you slipping. So if you didn't catch that mistake on your own, shame on you, but I did it on purpose. So anyway, I can still try to get my my 40s to match up, but let me just multiply by a negative 5 over here instead. All right, so my first one is going to be negative 40y, and my second one is going to be 136z, and 27 times 8 is 216. Okay, and then my other equation, if I multiply all terms by negative 5, I'm going to get 40y, and 22 times negative 5 is negative 110z, and 38 times negative 5 is negative 190. Okay, so back to my system of two equations and two unknowns. The y's are going to go away. The 136z minus 110z is 26z, and 216 minus 190 is 26. Isn't that convenient? So therefore, z equals 1. Okay, so that's a third of it right there. Remember, I'm looking for an xyz triplet or xyz point that makes all of the equations true. So at each one of these steps, as I whittle down and get rid of letters at a time, I'm creating true statements the whole time. So if z equals 1 works here, then z equals 1 works all the way back up to the start. Okay, so to work our way back up to the start, let's just deal with z equals 1 in just this situation and figure out what y is. Okay, I can put z equals 1 into any of these places. You can put it into here, or here, or here, or here. Any of the equations that relate y and z, I can put z equals 1 and get the y that goes with it. So actually, why don't I use this one up here? Negative 5y plus 17 times z, which I now know is equal to 1, equals 27, which means that negative 5y, and I'm going to subtract 17 from both sides and get 10, and it turns out that y is negative 2. So once you know one of your values, the second one is considerably easier to solve for, and then same deal for the last one. I need to know what x is. All right, so I have relationships for x, y, and z, and that's my three original equations. So take the two values you know, which are y is negative 2 and z is 1, and put those into any of the three original equations. I'm going to choose the middle one without that green negative 5 on it, because that's the one that just has an x. It'll save me one step in the long run. Okay, so to finish this thing up, my second original equation was x plus 3y minus 5z equals negative 7. Now the new info that I have is that y is negative 2 and z is 1. So if I put all this together, x minus 6 minus 5 equals negative 7, which means x minus 11 equals negative 7. And I'm going to plus 11 both sides, and it turns out that x equals 4. Okay, so all of that together, here's my final answer. X is 4, y is negative 2, z is 1. Final answer. This is the one unique point that makes all three of my original equations true. Okay, so I know that's a lengthy process and longer video than usual, but I might even show you a faster way to do this in class, but you got to learn how to do it the hard way first. So I will see you in the morning. Thank you for watching. Young out.